Hello everyone and welcome to the course on simulating fluid flows using Python. A very warm welcome to everyone who have joined us this particular week, and I hope that you can cover on all the stuff that we have discussed so far. To sum up briefly, we have looked at finite differences and we have looked at forward, backward and central difference schemes, and we tried to evaluate the first and second derivative using these schemes. The idea was, because we used to have a partial differential equation that governs the fluid flow, which we still do, and because our computers can't really solve, or even analytically we can't solve these differential equations, so we wanted to convert these differential equations into algebraic equations. So if you look at the expressions here, we could convert the partial differential equations to algebraic equations using finite differences. But because the majority of the stuff that we are going to talk in this course is oriented on finite volume methods, and that is why in this lecture I want to introduce the finite volume methods. So I'll start by highlighting what are the critical differences of a finite volume method from FDM, that is the finite differences. And we'll talk about the ideology of finite volume method as to how they are really evolved. So for example, we saw that in order to get the finite differences, we take the help of Taylor series expansion, and that is from where we can develop all the various formulas. So in the same way, we'll try to understand what is the building block of the finite volume method. Finally, we'll see how we can use that idea, how we can use those concepts and apply it to the same one-dimensional heat conduction problem that we were looking at in the last lecture. So if you haven't watched that last lecture, please check the link in the corner. This is very important because a lot of content in today's lecture would be taken from the ideas from the last lecture. In the second part of this lecture, I'll talk about how we can write a code for this particular problem. So I'll not go about in the coding part, but rather I'll give an idea of how we can formulate the algorithm. So you can say that in words, we would talk about writing the code. We would talk about the general structure of code without actually writing the code. So this is called as algorithm that we would be using. So it is going to be a very interesting lecture. I hope you stay here till the end. So without wasting any further time, let's get started. So let me start by highlighting how we can move from a finite differences approach to a finite volume methodology. So we'll consider the same physical domain that we were doing in the last lecture. That is a one-dimensional system. You can think of it as a rod. So we said that when we wanted to evaluate the temperature distribution here using a finite difference methodology, we had to divide this domain into a computational mesh. And when we did that, we defined a series of points where some of the points were defined on the boundary, that is the left and rightmost point here in this bottom picture, and we had some points interior to the domain, that is the 4 points sitting at the between those boundary points. So in finite differences, our idea was to get the value of function at different node points or different grid points, and we were not really concerned about the variation of function between these grid points. So if these two are my grid points, I wasn't really bothered about how the function is varying in this space. My only issue was, or my only concern was, to get the value of function at these points. And this makes sense because the derivatives evaluated using the finite differences, they need the value of the function at grid points only. So we don't really need to bother regarding that. So when we start to talk about finite volume method, we consider the same grid point. So this could be an arbitrary grid point somewhere in the domain, and we say that in the finite volume method, we consider a volume about that grid point. So you can think of that the grid point is the centroid of that volume. So in a three-dimensional system, the dimensions of that finite volume could be dx, dy and dz corresponding to the Cartesian xyz system. So again, if I want to discretize, now we want to understand how we will convert the same physical domain using the finite volume method. So there could be a number of ways, but I'll talk about the two very common techniques. The first one is we take the same domain, we put on the finite difference mesh. So you can see that the blue points, the blue grid points, they are exactly the same as we had defined that in the finite differencing system. But here what we do is we substitute a finite volume around every point. So I have put 4 finite volumes around 4 interior grid points here, and because the nature of system here is such that the boundary points would also have a finite volume, but the volume itself, it would be half because it wouldn't fit the entire domain. So that is why the volume itself would be reduced. So the interior points, they would have a full finite volume around that, but the boundary points, they may have to do some special treatment because their finite volumes are lesser in size. Another way in which we can do the discretization here is we take the same rod here, but rather than having the same underlying grid, we displace the grid slightly so that the rod has now equal number of finite volume or equal size of finite volumes, but accordingly the grid points has changed. Now, if you look at the top and bottom picture, that is the two different kind of finite volume discretized pictures, you will see that the total volume is fine. We have a total of 5 different finite volumes in both of these pictures, but the top grid has 6 number of points, whereas the bottom grid has 5 number of points. Also, if you'll observe, in the top picture, we have points exactly at the boundary, whereas in the bottom, we don't have points at the boundary. So you can imagine that in case where you have boundary conditions such that the boundary value is defined, then it would be advantageous to use the first kind of formulation. Also, if rather than the boundary value, you would have a boundary flux. We would talk about that later, so don't get scared just yet. Whenever we would talk about boundary flux, then the second type of formulation would be more advantageous. So I want to give you a heads up that there could be a different ways in which we can use the finite volume, but for majority of the course, we would be sticking to the first approach. So the idea is, because the finite differences and finite volume, using the first approach would be very interchangeable, as we would see very shortly. So that is why we would be using the first approach. So having understood that how the physical domain would be divided into the computational mesh using the finite volume method, let us understand the basic methodology of finite volume method. So we would consider the same physical phenomena being governed by one-dimensional pure diffusion equation. So when we were talking about the finite differences, we took the example, or we approached this problem using Taylor series, and we considered a general grid point indexed by I. So remember, from index we say, or we mean the count of that point. If you can't recall it, please go here and check the lecture, that would be very useful. And after applying central differencing, we saw that the temperature at this point I, it was nothing but the average of its neighbors. So this was the methodology of finite differences method, in which we use the Taylor series expansion in order to arrive at an iterative formula. However, in case of finite volume methods, the idea is that we consider the finite volume around the grid point. So here my grid point of interest is I. And just like before, I have two neighbors that I'm calling as I minus 1 and I plus 1. And when we define a finite volume such as this, you would see that because the finite volume, the extent of the finite volume is usually the same as the grid spacing. So if the grid spacing is 1 meter, the finite volume would also be 1 meter in width. So now if I have to center the finite volume around my grid point, it would lie somewhere around the midpoints between I and I plus 1 on one side and I minus 1 on the other side. So we call these faces where the finite volume is intersecting the grid as east and west faces. Accordingly, we call them as small e and small w. So that is how we represent a finite volume in a general system. The fundamental principle of using finite volume method is to take the governing equation and to simply integrate it over this finite volume. So that's what I've written on the top, that the governing equation is integrated over the finite volume, where the finite volume is defined as this purple space that goes from small w to small e. So we take our equation, that is d square t over dx square as 0. We integrate it with respect to the volume. So that is important. We have to integrate it with respect to the volume, which could be a three-dimensional entity. So here, because we have a one-dimensional system, so we can conveniently replace that with respect to integration to x, and accordingly we can have the limits going from small w to small e. So we integrate it over the control volume, and the integration goes from the west face to the east face. Now we can look at this integral. So because we have a second derivative sitting inside the integral that is going on with respect to x, and the derivative is also with respect to x. So recall from your calculus that we can simply take away the integral and we can integrate the second derivative, that becomes the first derivative, and taking in the limits we get dt over dx defined at the east face minus dt over dx defined as the west face is equals to 0. So here, depending on how we assume the variation of function between two grid points, we can numerically approximate the derivatives. So suppose we have this point as I, this point is I minus 1, this point is I plus 1. So when we write dt over dx at east face, that is the face lying midway between I and I plus 1, we can have any kind of variation here. So that is why when we were saying about finite differences, we are not really bothered about how the function varies. That doesn't really hold true in finite volume. Because if the function is linear, we would have one kind of derivative. If the function is a different polynomial, it could be another kind of derivative. So depending on how the function might vary between two grid points, these derivatives might change. So a good starting point to tackle this problem is to assume that the function varies piecewise linearly between any two grid points. The grid points word is more important. So suppose if I have my same domain here, I have my I plus 1 and I minus 1 points, and we can now consider all the grid points. So on the top, I'm plotting how the function might be varying. So if you observe, between any two grid points, the function is behaving linearly, and therefore, if I talk about these points, small e and small w, we can very simply write. So considering the point small e, because the function varies linearly between small I and I plus 1, we can write the derivative at small e being equals to t of I plus 1 minus t at I divided by h. This is, you might think that this is a straight line slope. This is true, but you can also derive this from the Taylor series expansion. So suppose if this is I plus 1, then you can say that this spacing is h by 2, this spacing is h by 2. Then if you represent the first derivative here, this formula is nothing but the central differencing of the first derivative, that t at I plus 1 minus ti divided by 2 times the grid spacing for this system, which is h by 2. And similarly, we can write the derivative at the west face as ti minus 1 divided by h. Remember that these are only true when the function is assumed to be piecewise linear. It could be a quadratic function, then it would be something else. We would look at quadratic functions later on, but for now, we'll stick with piecewise linear approximation. So now we have got the values of these derivatives in terms of the grid point values, and we can substitute it back to the integrated version of the equation. So once we substitute these values here, it is very easy to see that we can have the rearranged equation in the second form here. And if you further rearrange it to get the t at I, we get t at I as half of ti plus 1 plus ti minus 1. And if you are paying attention, this is the same form that we obtain for the finite differences as well. So there are no changes here, and we can definitely say that piecewise linear scheme would result in a similar equation that we obtained from the central differences. So I hope that this would give you an idea of how to get the finite volume methodology for a very simple system. We would later look at complex examples, but for now, this was to give you an overview. So to summarize, we first have to divide the domain into certain number of finite volumes, and then we have to integrate the governing equations over the finite volume to get their iterative formula. So in order to get that iterative formula, we simply integrate the governing equation over that volume, put the limits on it, and bang. So now we would look at the same example that we had considered in the past class, where we had a rod of length 1 and we had boundary points at a temperature of 0 and 1. So we had certain initial conditions that the temperature was 0 everywhere else except the right boundary, and the boundary conditions are as shown in the picture, and we were asked to calculate the temperature distribution at equilibrium. So now our idea is to get from these handwritten calculations that we did in the last class to a general code. So now I want to give you an overview of how we are going to write the code, but we're not really going to write the code. So we would talk about writing the code without writing the code. So in this numerical problem, if I want to define all the variables that we would be needing to define in the code, you can very easily see that we would have a few arrays. So we would have an array for the position vector because it's a one-dimensional system. So every grid point would have a different position or a different x location. So corresponding to that, we would have a position vector that I'm calling here at x, and corresponding to every position, we would have a temperature. So in this problem, we would have two arrays, one for the position and one for the corresponding temperature. So usually I define one temperature for the old value and one temperature for the new value. So remember, we are doing an iterative process where the temperature is being updated at every iteration. So it is convenient to define one array or one variable for that old value and one variable for the updated values or the new values. And in the similar way, there would be certain scalars that we would need to define. For example, we might need to define the total number of grid points that we want to divide the domain into. So that would go as n, usually represented by n. Then we can have the grid spacing. So again, that if you know the total domain length and if you know the total number of grid points, so in this way you can define the grid spacing or you can define the domain length. So accordingly, you can define any of the two variables because there are relationship between the three variables. And finally, for the iterative process, we have to define an error threshold because we would be defining iterations and we have to tell the code until when you have to do the calculations. So that's where this threshold would come into the picture, and we have briefly looked at this threshold in the last lecture where we were talking about the various convergence criteria. So we would define a particular convergence criteria while writing the code, but the code needs to know when to stop. So this is the threshold that would tell the code when to stop. So if I have to write an algorithm, so algorithm is sort of a pseudo code. So here, using the sentences and the words, I would try to write a general structure of the code. So when I would talk about writing the code, the first thing that we have to do is we have to define all the variables that we would be needing, and of course we might have to initialize them as such. So based on the initial conditions that we are given, so for example, we are given a physical domain, let us say from 0 to 1. So accordingly, we can define the x vector, and based on the initial conditions of the problem, we can initialize the temperature vector or the t vector. Now, when we got these initializations done, then the part comes about the writing of the code itself. So remember, the first thing to tell the code is until when you have to run, because otherwise the code might not understand. So the first thing that we have to do here is tell the code while the error is larger than the required error. So I have highlighted while here, and the reason is we would be using the while function. So we would use this function called as while that would compare our numerical error to this threshold error, that is epsilon. And if that criteria is met, then is fine. But if the criteria is not met, that is, if the numerical error is larger than the epsilon, then the code would continue. So if the criteria is not satisfied, then we say that for all the grid points, and here we would be using something called as a for function. So remember, in iterative processes, we have to iterate for every point. We have to go from the first point all the way to the last point. And that is where a statement like for is very helpful, which goes from all the points. So it says that for all the grid points, perform the iterations to calculate new values. So when we would be talking about for loop, within the for loop, we would have this iterative formula that we had arrived on using both finite differences and finite volume method. And after getting the new values, we would calculate the revised error, because the error would change after updating the values. So previously the error might be 50, but once you do the calculations, the error might go 20. So we have to calculate the error after updating the values. So once we do that, we'll again continue, and this part goes on something like we calculate the revised error, then we again go to the while statement. So the while statement is checked again, and if the statement is satisfied, then the error is less than epsilon, then we are good. But if that is not, then we'll keep doing this process. So that is what is called as an iterative process. I'm not expecting that you'll 100% get what is written here if you are a very beginner, but I hope that you get an idea of what we are trying to do through writing the code. So far we have looked at the algorithm. In the next lecture, we would look at the coding process. So we would get on in Python and we would try to write the code there. So if you can, please give it a try. Even if it's not correct, try to at least define those arrays, define those scalars, because we have looked at in the previous Python tutorial. Please go back to lecture 3 where we defined various kind of arrays and scalars. At least you should be able to do that. Then we'll talk about while and for loops in the next lecture. Until then, please take care. The coronavirus is spreading very rapidly in some parts. I hope you stay with me till the end of this lecture series and not just leave us in the meanwhile. So please take care of yourself, and I'll see you in the next lecture.